All right, welcome back to Rock the JVM. I'm Daniel, and in this video, I'm going to talk about Scala 3. And in particular, I'm going to talk about match types in Scala 3, which is a completely new feature. Now, for this video, I'm going to assume some familiarity with Scala 2 fundamentals, and in particular with generics, because we're going to use them in this video. Now, as recommendations, I'll recommend that you code with me in this video, and whenever you need to refresh your memory about match types, just refer back to this video or to its written form at the blog, with the link in the description. So without further ado, let's get to our code and let's see what match types are all about. And here I am in a Scala 3 project in IntelliJ IDEA. And if you have a pretty recent version of IntelliJ IDEA, you can create your own Scala 3 project by clicking File, New Project. And from this window, you can select Scala and here Dotty Experimental, because at the moment of this recording, the version of Scala 3 is not yet finalized. And so we are experimenting with a version of Dotty. And after that, you can click on Next, and then the wizard will be straightforward. Cool. So assuming that you have one of these in your window as well, I'm going to start by describing the problem that we want to solve with match types instead of describing the feature. So let's assume that you're working on a library on standard data types, for example, ints and strings and lists and so on. And you want to write a piece of code that extracts the last constituent part of a bigger value. For example, the last part of a big int, for example, is the last digit of that big int, assuming that big ints are composed of digits. So last digit of type int, for example. And for strings, the last constituent part of that is the last character. And for a list, you want the last element. Okay, so we want to create functions here that will return the last constituent parts of either big ints or strings or lists. And for these purposes, you might want to create some methods that look something like this. I'm going to define a def. Let's call this last digit of, and I'm going to pass a big int, let's say number, as a big int, and I'm going to return an int, and I'm going to simply say number mod 10, and then I'm going to convert that to an int. For a string, let's call this last car of a string as a string. And here I'm going to return a car, and I'm going to say if string is empty, then I'm going to simply throw a new no such element exception, because an empty string does not have a last character. Otherwise, I'm going to say string car at and say string length -1. So notice that I'm using the Scala 3 notation here, if and the condition without parentheses, then the expression, else whatever the other expression. All right. And increasingly on the Rock the JVM channel, I'm going to use this Scala 3 syntax. Now for a list, let's say last element of a list as a list of t. Let's make this super generic. And I'm going to add a type argument here, and I'm going to return a t, and I'm going to have a similar logic. So if list is empty, then I'm going to throw new no such element exception. Otherwise, I'm going to say list.last. Now, because we Scala programmers are a little bit of an OCD and we are maniacs of the don't repeat yourself principle, you notice that the signatures of these methods are very similar, and all of them have the meaning of the last piece of a bigger thing. So you'd like to reduce this 3-method API to one grand unifying API, which can ideally work for all types. And besides that, because you want to think about the future, you'd like to be able to extend this logic to other types as well in the future, perhaps some that are completely unrelated. So how can you do that in the current Scala 2 thing? How can you unify these 3 methods that will have a single signature and work a different piece of logic depending on the types that you get as arguments? Now, there is some good news and some bad news. The bad news is that for Scala 2, you can't do that. Sorry. And the good news is that it's possible in Scala 3. Now, the only way that we're going to be able to solve this in Scala 3 is for you to smash that like button and subscribe to the channel, because it helps me a lot and it helps you become a better programmer. Anyway, and in Scala 3, we can define a type, an abstract type here, an abstract type member of the object that I've defined earlier in this video. And this type member can reduce, that is, it can become a concrete type depending on the type argument that I am passing. So for example, I can define a type. I'm going to call this constituent part of, and I'm going to use a type argument here. I'm going to use the notation t, the t meaning the bigger thing from which I want to extract that constituent part. So t can be a list of ints, t can be a string, or t can be one of those big ints that I'm using here. And I can write the following, and this is new in Scala 3. I can say t match, just like I'm using a pattern match but on types. And here I can indent myself and add a bunch of cases here. And in case I get a big int, the constituent part of a big int is an int. In case I get a string, I'm going to return a car. And in case I get a list of a variable type argument small caps t, so look at this guy, I'm going to return that particular type. So notice that the small caps t is a type variable here, and this expression is not actually an expression, but it's a type level reduction for the compiler, so that the constituent part of t can become whatever this expression will give you. So for example, I can define a digit, which is a constituent part of big int, which is the same as int, and on the right hand side I can put in 2 here, and this is okay because the compiler type checks the right hand side with the left hand side, which is the same as evaluating this pattern match at the type level. All right, I can define, for example, a character as a constituent part of string, and on the right hand side I can put in a character, and let's use an element of a list, an element as a constituent part of list int. So notice that I'm passing a concrete type here, list int, and I can pass the value 42 here, which is an element of list int. All right, so all of these are type checkable. So I hope you get the picture. Let's see how it can solve the previous first world obnoxious OCD kind of problem that we used to have. So I'm going to define a method that's called last component of. This will take a type argument t, meaning the bigger value that I want to extract the thing from, and I'm going to say bigger value of type t, and I'm going to return the constituent part of t as the last element of that bigger value. Right now I'm going to put question marks here because we're going to implement that in a minute, but assuming this were a thing, I would be able to use, say, for example, last digit of a big int would be last component of big int with a huge number here, and this would be the integer 5. And if I said last character as last component of the string Scala, this will be the character a. If I wrote last element as last component of, let's say, the list 1, 2, 3, this would be the element 3, which is an int. All right, so last component of would work with all of these completely unrelated types, and this method would return the constituent type of that particular value given by the pattern match that we wrote earlier. Now, let's move on to the implementation of this method, because such a method can be implemented, and it can be implemented by following this exact pattern matching on type level at the value level. So I'm going to say bigger value match, so a simple pattern match, and I'm going to use the Scala 3 indented syntax, and I'm going to say case b of type big int. Then I'm going to return, let's say, b mod 10 dot toInt. All right, case, let's say s, which is a string, I'm going to return the expression given by that if else statement. So if I say s, if s is empty, then throw new no such element exception, no. Okay, otherwise I'm going to return s car at s length -1, and in case I get a list, let's say list of underscore, which is a placeholder for a list of anything, I'm going to run the same logic. So I'm going to say if L is empty, then throw new no such element exception, otherwise L.last. All right, so notice that we followed all the logic that we stored in 3 different methods, and we now have a single one which can work for all the values. So this is how we can solve our first world problem of unifying 3 different methods under the same API with a match type. Now, a good question would be, why would we need these match types to begin with? And the general answer would be something like this. Match types are useful to be able to express methods that are returning potentially unrelated types, which are dependent on the input types, much like we had here in the example, which can be correctly type checked at compile time. Now, this was all very abstract, so let's draw some distinctions to what you may already be familiar with. So, for example, a sub-question of that would be, why is this different from the regular OOP? The reasoning being that in standard object-oriented programming, we have hierarchies of classes, and we can program against an interface and at runtime return different types. So for example, I would be able to say, let's call this return last constituent of, and I'm going to pass a thing which is of type any, and then I can do pattern matching on this any, but the problem is, or the idea is, that I'm returning one big constituent part, assuming that I've defined this as a trait or as a higher level interface. All right, so I would define this constituent part as a trait or as some kind of parent type to all my constituent parts, for example, constituent part of int, of string, and of lists. All right, and then I would be able to say thing match, and then return the appropriate real constituent parts belonging to that particular thing. So this is the Java style way of returning potentially different things at runtime. So you lose the type safety of your API because the real instance is returned at runtime. Now at the same time, the return types must all be related because they must all derive from this constituent part mother trait. All right, so you lose type safety because the thing that you're passing here can be of any type. All right, so you have to support big ints, strings, and lists of int, which can only be rectified by using any here, and all the types are related and different only at runtime. So the compiler can't help you in this case. Good, so that was the first sub-question. Now, why is this different from regular generics? Now, this is a more nuanced question because generics are used for exactly this kind of purpose, to be able to reuse code and logic on potentially unrelated types. And this is what I said. The match types are used so that we can return potentially unrelated types here at compile time. Now, this is a better question and also more subtle. And that is because generics themselves are used for type checking as well. So let me give an example. Let's take the method that returns the last element of a list. So I'm going to define, let's call this last element of, and I'm going to pass an argument, let's call this a, and I'm going to use a list as a list of a. And this returns an element of type a, which is list.last, much the same as we did earlier. We can also check for empty and so on, but just look at the method signature. So I'm going to use last element of, let's call this last element of list because I used this name earlier. Cool, so I have this method that is generic in the type A, that given a list of A returns an A, right? So I can say last element of list, and I can use list 1, 2, 3, and this would return the 3, which is an int, right? And I can say last element of list, and I can use list of A and B, and I would return the string B, which is obviously a string. So if you take a look at this method, it also returns potentially unrelated types because it can return an int or a string depending on the argument. But the difference here is that this particular method makes the compiler do a direct relationship between the argument type, which is a list A, and the return type, which is an A. So if you are given a list of int, the compiler knows immediately that you are going to return an int. So basically what you're saying to the compiler is that this method takes a list of A and returns exactly an A and nothing else. On the other hand, this method that we wrote here at line 30 allows the compiler to be a little bit more flexible in terms of the return type, depending on the type definition of the return type, this constituent part of. So you're basically saying to the compiler that if the method takes a string argument, then it returns a car. So this thing. If it takes a big int argument, it returns an int. And if it takes a list t argument, it returns a t. So you allow the compiler to be more flexible with the returned type, not necessarily have a direct relationship between the argument type and the return type in this way. So I hope I've made this distinction reasonably clear, because when you see this kind of code directly in front of you in production or whatever, it's really hard to see this distinction. So expressed in this way, we can see that the connection between the argument type and the return type is a little bit more loose to the compiler, but still properly covered by this type level pattern match, which would have been impossible to create using regular generics. All right, so let's move on. I'm going to talk about recursion of match types, because match types can be recursive. For example, if we wanted to operate on nested lists, we would write something like, let's call this type lowest level part of, and I'm going to use a type argument t denoting the bigger thing that I want to extract the value from. And I could say t match. And in case I get a list with a type argument lowercase t, I would return lowest level part of that particular type argument t. So if I had lists of int, pattern matching would go against list of int, and then it will return lowest level part of list int, and then the pattern match would run again, and then we would return an int. And I'm going to demonstrate that shortly. And in case we got anything else, you can use a wildcard here and you can return that same t. So let me give an example. Let's call this last element of nested list as a lowest level part of, and I'm going to use a list and list int, and as a potential value of this I can use 2, for example, because 2 can be an element of list int because it's so nested. So notice that the compiler will allow you to write recursive definitions of type members using match types. However, the compiler will detect cycles in your definition. So for example, if I write something like type, let's call this annoying match type, which takes a type argument t, and this is t match, and in case I get something, I'm going to return that same annoying match type with that same type argument t. This would be impossible to create because the compiler would say illegal cyclic type reference, the alias whatever is referencing itself in its definition. So this is not okay. Okay, good. Also, the compiler will also detect potential infinite recursions or very, very deep recursions in your match type. So for example, if I define, let's call this infinite recursive type with a type argument t and say t match, and in case I get an int, I would simply call infinite recursive type of t. And instead of val, I would use a type because we're operating at the type level. All right, now this is compilable, but if I try to actually use it in a real use case, for example, if I define a method, let's call this a naive method of t, which returns an infinite recursive type of t. Let's give some dummy implementation here. The implementation is not that important, only the signature of the method is. And let me try using that. So I'm going to say val, let's call this illegal, of type int as a naive method with type int. Now, this would be an error, and IntelliJ would signal that right before the type parameter here. And we have recursion limit exceeded. Maybe there is a illegal cyclic reference. That is because the compiler will internally run the match type here, and it will stack overflow. So the compiler will inherently run into a stack overflow and surface that into a compiler error. All right, so this is something that you should also bear in mind. Not okay with infinite cycles. The compiler stack overflows. Now, The final thing that I will say about match types is that they're, right now at least with Scala 3, pretty limited, because as far as I'm aware, and please correct me if I'm wrong in the comments, the utility of match types independent methods such as the last component of that we wrote earlier is conditioned by the exact signature of the dependent method. So far, only methods with this particular signature are allowed here by the Scala 3 compiler. So it needs to take a value of type t and then the match type appropriate to the argument type, and the structure of the method needs to be exactly identical to the match type of the type definition. So I would have to exactly say bigger value match and then run all the cases that are specified in the type level pattern match as well. So the value level pattern match would be identical or mirrored by the type level pattern match that we wrote for the match type. Otherwise, the code will not compile. So for example, if I wanted to do something useful with a match type like accumulate, and I'm going to use the type, the argument type t denoting the bigger thing, and I'm going to say accumulator of type t and a smaller value, which is a constituent part of t. And finally, I would return a t. Now, this kind of method is not implementable at all. So the only implementation that I can give to this method is triple question marks. If I try to say, let's call this accumulator match, and in case I get b of type big int, I would return b plus smaller value. This would not be possible because smaller value is a constituent part of t, it's not a constituent part of big int. So at this point, the compiler loses track of the fact that smaller value is a constituent part of big int. So with this pattern match, the compiler is unaware of the fact that t is equal to big int. So this is a current limitation of the Scala compiler. If that were the case, if the compiler were able to equate t with big int in this exact scope, right here after the right-hand arrow sign, then that would be equivalent to the so-called flow typing. And flow typing means that the compiler is able to deduce the exact type of a value as the scope advances. So for example, in this particular case, it's obvious that t is equal to big int for this particular expression. And only a handful of languages are able to cover flow typing. For example, TypeScript is a famous example, and Scala 3 at this point is unable to do that. Well, it remains to be seen whether future versions of Scala 3 will be able to cover flow typing. That would be awesome. So I hope you liked this video and found it useful, and if you did, go ahead and click the like button for me and subscribe to the channel for more videos like this coming your way, and follow me on Twitter and LinkedIn because I post fresh updates on upcoming material. Now, I'm dying for feedback, so please leave your comments below. I read every single one, and check out the Rock the JVM website. I have tons of content for you and courses on Scala and Akka and Apache Spark and so much more. Until next time, I'm Daniel, signing off.